This mini-lecture discusses precipitation reactions, including how to predict the products of a double displacement reaction, how to predict if a product will precipitate, and how to determine the net ionic equation for a precipitation reaction. A precipitation reaction occurs when two solutions of soluble ionic compounds are mixed and an insoluble solid, called the precipitate, is formed in solution. When looking at a precipitation reaction, note that this is a double displacement reaction where we can predict the products by simply switching the anions in the two ionic compounds or by switching the cations in the two ionic compounds. Either way, products are predicted by considering the number of ions needed to balance the charges in each new combination of anion and cation, and then the precipitate is identified as the product that is insoluble in water, which can be determined by referring to the solubility rules described in the last mini-lecture and provided on the back of the periodic table for our class. State labels are critically important in precipitation reactions, as all ionic compounds that are soluble are given the aqueous state label, so that those reading the reaction know that the ions in these compounds fully dissociate, existing separately in solution and not bonded to each other. Whereas the precipitates stand out as the only ionic compound in the reaction with a solid state label that will not dissociate into ions in solution. An insoluble solid that precipitates is immediately obvious in an experiment, appearing as a cloud of opaque material at the point where the two aqueous solutions of soluble ions initially mix. This cloud of precipitate is composed of very fine ionic crystals that slowly disperse into the rest of the solution and can turn the entire solution cloudy and opaque. While it may seem like the precipitate is dissolved in solution as the solution can take on a uniform color, this is not the case on the molecular level. A true solution contains ions of ionic compounds that have dissociated and therefore are fully separated from each other, whereas the opaque cloudiness of a precipitate is composed of a temporary suspension of very tiny precipitate crystals, where the ions are actually bonded to each other, creating the ionic solid. These small precipitate crystals are temporarily suspended in the solvent due to their very small weights, but given enough time, they will eventually settle to the bottom of the test tube, proving that this is not a true solution. In fact, test tubes containing precipitates are often centrifuged or spun around, a process which utilizes centrifugal force to rapidly settle the small precipitate crystals at the bottom of the test tube, so that the supernatant solution containing any remaining soluble ions can be poured off, and that precipitate solid at the bottom of the test tube can be washed and collected separately from the solution. I already briefly described the steps in writing a precipitation reaction, but here's an example broken down in detail. Let's say a problem asks you to write the reaction that occurs when aqueous solutions of potassium chromate, or K2CrO4, and barium nitrate, or BaNO3 are mixed. Sometimes you will be provided with the molecular formulas. Other times you may need to determine the molecular formula first from the provided name of the ionic compound. So now's a good time to start brushing up on your nomenclature skills in preparation for problems that give names instead of molecular formulas. Once the chemical formula of each reaction is known, we consider the ions that are present in these aqueous solutions. Remember that if the ionic compound is labeled as aqueous, or if you are told you have an aqueous solution of the compound, then the compound itself does not exist as the chemical formula implies, but rather it exists as separate ions in the solution. We know this because we interpret that aqueous label, or the term, to mean that the ionic compound has fully dissociated into separate ions. So for the potassium chromate solution, there are 2 potassium cations for every 1 chromate anion. And for the barium nitrate aqueous solution, there is 1 barium cation for every 2 nitrate anions. Again, the ratio of the ions in the ionic compound is preserved for the mixture of ions in solution. Next, we consider the possible products that could form if the ions undergo a double replacement reaction. In this example, I switched the cations, but you would predict the same products if you switched the anions. Keep in mind that when predicting the products from these new combinations of ions, we want to make sure that the ionic compounds are neutral. So we are looking to balance the charges. Barium with its positive 2 charge only needs one chromate with a negative 2 charge to form a neutral ionic compound. So the product, barium chromate, contains one of each ion. Potassium with its positive 1 charge only needs one nitrate with a negative 1 charge to form a neutral ionic compound. So the product, potassium nitrate, also contains one of each ion. But there are 2 potassium ions and 2 nitrate anions in the original reactant compounds. So technically, in order for the products to be balanced in this reaction, we note that 2 units of potassium nitrate are formed for every 1 unit of barium chromate, as each potassium cation, since we have 2 of them, combines with each nitrate anion to form 1 unit of the ionic compound. However, the cations and anions will only combine to form precipitate if this resulting compound is insoluble. So we now check the solubility rules to see if either of these products is insoluble in water and will therefore precipitate from the solution. So take a moment to pause the lecture and look at the solubility rules chart and see if you can predict whether either proposed product will be insoluble in water. Ready to review? All right. In the steps we've completed so far, we've basically determined the balanced precipitation reaction. So I've included this at the top. Now we are considering the state labels for the 2 products. Looking at the solubility rules, note that chromates are usually insoluble, and the barium cation is not one of the soluble exceptions for chromates, whereas potassium and nitrates are both usually soluble. So based on these rules for chromates, we expect the barium chromate to be insoluble and form a precipitate, whereas the potassium nitrate would be soluble, and this would be the case due to either the potassium ions or the nitrate ions. Note that it is not crucial that both ions are soluble for the compound to be soluble, and any compounds that contain potassium ion will be soluble, just as any compound that contains nitrate ions will be soluble. In this case, this is just a double whammy of solubility, and this means that the solution will still contain potassium and nitrate ions as they will remain fully dissociated due to their solubility. But the barium chromate will definitely form a solid precipitate and settle to the bottom of the beaker as it is insoluble. Finally, I'll just point out that when conducting this particular reaction, we can use observational clues to predict the identity of the precipitate, because chromates are usually yellow, and the solid precipitate that forms in this reaction would also appear yellow, further suggesting that the precipitate contains the chromate and must be barium chromate. So when conducting precipitation reactions in the lab, see if you can pay attention to observational clues like this to determine what the precipitate identity should be. Now, some students will prefer to wait to balance the precipitation reaction until after they have determined the precipitate. And this is totally acceptable and often a better approach, as it ensures that you focus simply on predicting the products based on balancing the charges of the ions, rather than by considering the number of each ion that the reaction starts with. In this case, you would have determined the unbalanced precipitation reaction as given here, and then you would balance this reaction by adjusting the coefficients as needed, remembering that when balancing a reaction, you do not change the subscripts, as that would change the identities of the compounds themselves. We simply want to adjust the number of each compound in the reaction, not the composition of the compounds. In this case, we simply need to add a coefficient of 2 to the potassium nitrate product. We can go even further with this precipitation reaction by determining the Net Ionic Equation, which highlights only the ions that are forming something new and ignores those ions that are still dissociated in solution after the precipitate forms. In this case, the potassium and nitrate ions are the ones that are ignored. To wrap this up, let's look at one more example. And this time we'll start with the balanced complete molecular equation for the precipitation reaction and determine the net ionic equation from this starting point. The first step is to consider that all aqueous compounds in the reaction exist as ions in solution. So we rewrite the reaction in a way that better represents how the compounds actually exist, and we call this the total ionic equation or reaction. Each ion is listed separately, and subscripts or coefficients from the balanced reaction that indicate multiple ions of one type are now used only as coefficients. For example, barium nitrate reactant contains 2 nitrate ions, as indicated by the subscript in the molecular formula. So the total ionic equation indicates the 2 nitrate ions by placing a coefficient of 2 in front of the nitrate ion symbol. The same thing occurs with the sodium ions in the sodium sulfate reactant. In the case of the sodium nitrate product, since there is a 2 coefficient in the balanced molecular equation, then both the sodium ion and the nitrate ion will have coefficients of 2 in front of their ionic formulas to indicate that we have 2 of each of these ions. All of these ions get the aqueous state label, and we indicate the charge on each ion as a superscript. So a total ionic equation should have ionic charges indicated, unlike the molecular equation, which lacks any indication of charges. The barium sulfate precipitate is the only compound formula that remains the same, as the solid does not dissociate and therefore does not exist as ions in solution, and it retains its solid state label. Next, we eliminate the spectator ions. These are the ions that remain in solution after the precipitate has formed, and they are called spectators because they do not participate in the reaction. They can be identified by looking for ions that are the same on both the reactants and the product side. So the 2 sodium ions and the 2 nitrate ions are going to be our spectator ions for this reaction. Everything that remains comprises the net ionic reaction, and if you have done things correctly, the net ionic reaction should also be balanced by the end of this process. This concludes the 4th mini lecture for Chapter 8. Please note any questions you may have about this material and how it is utilized to solve problems in the suggested end of chapter exercises and the sapling homework for this chapter. Please post any urgent questions on Piazza. I will also take questions on this material during one of our required class meetings, and during that time we will focus more on problem solving for concepts in this chapter.